Let us discuss another law that involves gas laws, and in this law, it's called the combined gas law. The combined gas law. Why is it called the combined gas law? It's because it's a combination of Boyle's law. Okay, we talked about Boyle's law, which was PV equals to a constant K, and then there is Charles's law, which was volume over temperature in Kelvin is always a constant. Volume is directly proportional to temperature. Boyle's was pressure is inversely proportional to volume. And then there was Gay-Lussac's law, where we were comparing pressure and temperature to give us a constant K. Now you see the left side here seems to be always a constant. So we can say PV, which is seen in Boyle's law, the V is seen in Charles' law, and the P is also seen in Gay-Lussac's law. So PV on top over the T is always the denominator, is gonna be equal to constant K. Let's misspell it with a K, with a K constant, okay? And if that is a constant, because we know PV by itself is a constant, V over T itself is a constant, according to one of these laws, then we also have P over T. Gay-Lussac's law is also a constant. We can combine them. So we combine them to give us that constant. And so we can take advantage of this and say P1 times V1, those are initial conditions of pressure and volume, divide by T1, initial temperature conditions, must be equal to a final or new conditions P2 times V2 over T2. We usually prefer the pressure to be in atmospheres, volume to be in liters, temperature in Kelvin. But we can work with other units for pressure and volume, but temperature has to be in Kelvin. The equation I just wrote here is now this. Okay, so all three gas laws are now combined into one equation. P1 V1 over T1 equals to P2 V2 over T2, where the P1 V1 T1 is initial conditions and P2 V2 is the new conditions. And that tells me that if I know 5 of these variables, so if I know 5 of these variables, I can find by calculation the 6th variable. So we'll take advantage of that and do some math. This equation is used for determining the effect of changing two factors, for example, pressure and temperature, on the third factor, which is volume. Let us do some example. Now let us do calculations of two examples illustrating the use of combined gas law. I'll remind you the formula for our combined gas law. Our formula for combined gas law is P1 times V1 over T1, those are initial conditions, must be equal to new conditions P2 times V2 over T2, where the temperature must be in Kelvin. So the question reads, a toy balloon has an internal pressure of 1.05 atmospheres and a volume of 5 liters. If the temperature where the balloon is released is 20 degrees, what will happen to the volume when the balloon rises to an altitude where the pressure is 0.65 atmospheres and the temperature is negative 15 degrees Celsius? So as usual, I always like to write my givens so I don't forget. So I have my initial pressure, because I'm told the balloon has an initial internal pressure of 1.05 atm. Do we have an after pressure? where the rises to an altitude where the pressure is 0.65. Yes, we do. So P2 is 0.65 atmospheres. And then I have an initial volume V1 of the balloon is 5.0 liters. And do we have a final volume? No. It's asking us for the final volume. It's saying what will happen to the volume when the balloon rises. So V2 is not known. It's actually needed. Now let's go to temperature T1. Initial temperature where the balloon is released is 20 degrees. So it's 20 degrees Celsius. Like I said, we have to convert him to Kelvin by adding 273.15. You always do that. That will be 293.15 Kelvin. And then I go on the other side and do T2. T2 is, let's see, what is T2? T2, the after temperature is negative 15 degrees Celsius. Again, to convert that to Kelvin, I add 273.15. This will give me, so 273.15 minus 15. This will give me 258.15 Kelvin. Okay, so now I have my everything. What is left for me to do is now to bring up my formula. P1 V1 over T1 equals to P2 V2 over T2. It looks like we need V2. So I have to find a way to make it the subject of the formula. So to do so, I will multiply both sides. We need V2, so I'll multiply both sides by the inverse of T2 and P2, so that this goes with that, this goes with that. I do the same thing on the left because what you do to the right is what you do to the left, so it will be T2 over P2 multiplied by the original expression. Here nothing is cancelling. So this will lead to this expression. My V2 will be equal to T2 over P2. Now we are multiplying the other factors like that. So now I can find my V2 based on this just by plugging in the numbers. So my numbers here are T2 converted to Kelvin is 258.15. If you don't convert to Kelvin, your answer is going to be so wrong. P1 is 1.05 ATM. And then our V1 is 5 liters. The initial volume is 5 liters. Then we are dividing this. We need to find the final volume of this balloon, toy balloon. Our P2 is 0.65 ATM. That's our P2. Our T1 in Kelvin is 293.15. If you do not convert it to Kelvin, you get it wrong. Now let us do the math and see what we get. So I have 258.15 times 1.05 times 5. Then I'm going to divide by 0.65. I divide by 293.15. So I'm getting 7.1126. We can see that. 7.1126. Now, what are the SI units? We can tell that the K and the K will cross out because they're divided. ATM and ATM will cross out because it's divided. We are left with liters, which is what you are looking for. We are looking for the later volume, the new volume. So that's correct. So if factors are changed, starting with pressure of 1.05, volume of 5, and temperature at 20 degrees for the toy balloon, this will be the new volume. Now, to report it to the correct significant figures, I see that I should be reporting it to, let's say, 2 sig figs, and that would be 7.1 liters for our final volume. Let us do another question involving the combined gas law. The question reads, a small research submarine with a volume of 1.2 times 10 to the power 5 liters has an internal pressure of 1 atm and an internal temperature of 15 degrees. If the submarine descends to a depth where the pressure is 150 atmospheres and the temperature is 3 degrees Celsius, what will the volume of the gas inside be if the hull, meaning the body of the submarine, breaks? The hull of the submarine is just the body of the submarine. So what will be the after volume? So looks like we need V2. We are given everything else. So remember, P1 is given as 1 atm, that's the initial pressure, and then P2 is given as, you see, it descends to a depth of a pressure 150 atm, and then we have T1 is given as 15 degrees Celsius. We'll convert that to Kelvin. T2 is given as 3 degrees Celsius. It's right there. We need to convert that to Kelvin. V1 is given as 1.2 times 10 to the power 5 liters. That's the volume initial. And the final volume is what we need. We need to calculate that. It's needed. So let me firstly convert my temperature from Celsius to Kelvin by adding 273.15. Okay, for this one it will be, I think this is 288.15 if I add those two, right? See, 273.15, we add 15. Yeah, and then here is just gonna be 276.15 Kelvin. Knowing that, we are going to do the math because we are aware of the formula for combined gas law. Looks like this. We again need V2. So we will write this equation to read. We did it before. I showed you V2 is found here, how to get it. So it's T2 over P2 and then the rest. T2 over P2 from that V2 side and then the rest. Just rearrange these variables. And then our T2 is supposed to be 276.15 Kelvin. It's right there. And then our P1 is 1 atm. And then our initial volume is 1.2 times 10 to the power 5 liters. All this is being divided by P2 T1. P2 is 150 atm. And then T1 is 288.15 Kelvin. Doing so, you cancel out the common units. Our SI units left is going to be in liters. There it is. And we do the math. Let's see what we'll get. So clear, 276.15. I'm multiplying by 1.2 exponent 5. And then I'm going to divide that by 150 and then divide it again by 288.15. The answer I'm getting is 766.68 liters. Yep, can't even put a 4 there, it doesn't matter. Looking at the question, we should report the answer to two significant figures. So doing so, we'll convert this to 7.66 times 10 to the power 2 liters. We need two sig figs. So in that case, I see this 6 is greater than 5. So I'll round up the underlined 6 to a 7. So it will be 7.7 times 10 to the power 2 liters. That will be our new volume, final volume, reported to the correct significant figures. So now here is a summary of the gas laws that relate to pressure, volume, and temperature. Number of moles is not included here. We'll talk about the relationship to number of moles in Avogadro's law relating to volume. So Boyle's law related P and V. As P increases, V will increase. Charles' law related V and T. As T temperature increases, you expect the volume to increase because the gas molecules are moving so fast. Pressure and number of moles is kept constant. Gay-Lussac's law, as temperature is increasing, you expect pressure to increase because of random movement again of those gas molecules. You're keeping volume and number of moles constant. Combined gas law combines all the other three on top. So the PV, V is here, P is there, is combined with the T. So PV is on top because it's always on top. This is like PV over 1, you know. PV, VV, PP, those ones are put all together here. And then the temperature is put down here. So you get P1 V1 over T1 equals to P2 V2 over T2. It combines Boyle's, Charles, and Gay-Lussac's law. Okay, here the number of moles is constant.